Okay, I think we can begin now.
Okay.
Yeah, so it is 9:30 now. So let me introduce you first. Uh,
Sure.
Dear participants, good morning. Today we are going to have a session on attention mechanism and its use cases by Dr. Santanupal. Dr. Santanupal did his BTech in computer science at Kalyani University and MTech from Jadavpur University. After that, he did his PhD from Saarland University, Germany, and he was a postdoctoral fellow at the Saarland University, Germany. He also worked as a researcher at Saarland Informatic Campus, Germany, and currently he is working as a architect at the Wipro AI Lab, Bangalore. So his research interests include machine translation, automatic post editing, multi-word expressions, question answering, and question generation, natural language processing, human-computer interaction, multimodal interface, multimodal machine translation. So with this brief introduction about the speaker, now let me hand over the platform to Dr. Santanupal. Dr.
Thank you, Vishwanath sir. So let's begin with attention mechanism and its use cases. Before starting, so now we can consult about what is attention. So actually, attention is not new. So as a term, so if you see on the left sides, you can easily identify a dog who is working, who is wearing some sweater and blanket on his shoulder. But how did we identify the dog? So we, in our brain, we have some features. It is automatically trained. So based on those features, so we can easily identify that this is a dog. So if you see the box, red box, and the yellow box, so based on these features, so we can identify this is a dog. But what happened if we only see this box, so the gray box, for example, on the rightmost figure. So if this question mark box, if it is not visible, then we can't say that whether it is dog or something other, or maybe it could be a human. And also our focus is not going through the background. So the background also, we can't say that. We can easily say that this is a dog, but we can't say that the dog is on the background, like some snowing floors, ground, or some forest on the backside. So our focus is only on this, identifying the dog actually. So this is mainly we can define attention. So it's focusing somewhere where we can easily identify or match the object. So before proceeding to attention in details, maybe we can introduce something about sequence to sequence model, like encoder decoder. So sequence to sequence model is following encoder decoder models, which was introduced by Sutskever in 2014. So it comes on machine translation and language modeling tasks. So that in this case, if you see this, this is the very first model for machine translation, which is sequence to sequence model, which can accept some source sentence, and it can generate the target sentence in some other language. So in this case, the source sentence is French, and the target sentence is English. So if you see each of the source word are presented in some representation, and these representations will be passed to a LSTM network, which is like a sequence to sequence design, like from one LSTM network to another LSTM. So, and each time and this one, every word is the step of this LSTM to another LSTM is called time step. So for each time step, there will be some information passing from the very first word to the end word, and at the end it will present some representation for the decoder. So encoder encode the entire source sentence and then present some representation, and based on this representation it will start the target word, like I hate this movie. So in this case, so this word, this representation, the end representations, based on this end representation, receive all the information from the source words, and then it will pass to the decoder. So there will be some disadvantage here. So it cannot be the if you consider the end uh, word, end representation can can accommodate all the information of the source word, then in that case there might be possibilities to forget from the beginning some information from the beginning. So there would be they have presented some context vector thought, that is also called thought vector. So here the encoder poses the input sequence and compress the informations into a context vector, and this context vector is generally a fixed length vector, and this representation is expected to be a good summary of making the whole source sentence. And then decoder take this summary and it is initialized and transform it to the output uh, on the desired language, or maybe the next word for language model cases. So here is the if you see the how encoder make the context vector. So suppose we have C is eating a green apple. In that case, the context vector will be generated in terms of some real value, and this based on this real value or based on this representation, and decoder take this one and generate the next word in a sequential order. So here there is a critical disadvantage in this case. So because so in this case the fixed length context vector is the same thing like the end sentence in end word presenting the information. So instead of the end word, there is an intermediate context vector now, and this context vector has the same problem to forget everything on the first part of the sentence representation. So this kind of representation, Ray Mooney said that you can't cram the meaning of whole sentence into a single vector. But if we represent this sentence for a single vector is a concatenation of all the words containing a sentence. For example, in this case, this is an example. So in this case, so before it was represented in a single vector, let's say it is the size of 3, and then in this case each word is represented as a single vector, and it is a concatenation. So it is a multi-dimensional vectors. In this case, it is two-dimensional, but in general, it was presented as a multi-dimensional vector. So in that case, there could be some possibility to remember the entire sentence. And before this, before proceeding to attention mechanism, so in this case, if the sentence are very small, in that case, this model are working reasonably good. But there is some problem if the sentence is very huge. In that case, there possibility to remember, to forget everything. Not everything, forget some information. So now the attention mechanism. Attention mechanism is generally born in translation domain. So in 2015, so it is like a span, like 2014 to 15, Badano was proposed attention mechanism, and it resolved some problems, this kind of problem for forgetting. So the secret sauce here, in this case, the shortcut between the context vector uh, and the entire source input. So in this case, the weights of these shortcut connections, shortcut is the context vector connections, are customizable for each output element. So while the context vector has accessed the entire input sentence, we do not worry about forgetting. So because context vector will be connected, we have the information of the all input words, okay, all input sequence. So there is no possibility to forget the beginning of the sentence. So as it was, we have seen last for the last slide, that at the end there is some possibility to forget the information of the beginning of the sentence. So it is actually providing the alignment between source and target, and it is learned and controlled by context vector. So here is the pictorial representation of attention mechanism. So in this case, if you see that this is a sequence of source input for, let's say, x1 to xn, and there is a bidirectional RNN, and where the one is forward, this one is the forward representation. So x1 information passed to the hidden layer, and it will be passing through the hidden layer, and also there is a backward representation. And if you see the context vector, it has always the connections of the all the hidden layers. So it has the information x1, x2, x3, and so on. So basically, this attention mechanism work with encoder hidden state, decoder hidden state, and the alignment between source and target. So these are the connections, the alignment between the source and target. So in this case, we are finding the alignment of YT of which one from x1 to xn. So this is the information provided by the attention mechanism. So for more details, so how it is working. So let's say x1 to xn are the input. It has vector representation, and it goes to the RNN for the forward representation, let's say HI. So for the forward, and the backward representation, let's say the backward HI. And this HI is calculated the concatenation vector. Let's say the vector size is 3, suppose, and this is also 3, and then it will be the size of the HI dimension will be the 6. So this input representation is then concatenated with the output representations with some weighted matrix are multiplied, and then after the hyperparabolic passing to the hyperparabolic tangent function and a vector linear representations of the vector, then it will produce some alignment score between the x1 x and the and the x1 and the yt. So during training process, it will see the example, and then these weights, this called weights, so w and v, and these are tuned during the training time. And then a softmax function, which is like e to the power the result of this score and all the other score provided by normalized by all the other score for x1 which are probable to align with yt. So this alpha ij is the attention score, uh, is uh, is then are where are then passed to the context vector, and this context vector are nothing. This attention score along with the hidden layers. So this is actually a weighted average of all the input hidden state. Okay, and then finally this decoder state use this the previous previous vector information and the current context vector, and also the previous word vector representation, and this function will generate the decoder state, and based on this decoder state the next probable word will be generated in sequence. So now maybe we can see more in more details with this figure, so that, so as I said, so this one is actually the forward and backward hidden state. So like this one is like a three-dimensional figure like this. So these are calculated simultaneously, and then h1 and h2 are concatenated. So in this case, two vector size 2, in this case it will be the representation of vector size 4, and then it will go to the scoring function here, the scoring function, and then this is softest function, so which can the probability, assign the probability between, this is actually the normalized or scaling factor, maybe you can say, like it the value will be between 0 to 1, so all the value are scaled with 0 to 1, and then this one is the multiplied with this alpha ij. Let's say here you have the information of alpha ij, and then it is multiplications, and those are normalized, so you can sum up all the ci. So to calculate ci, it is the sum of all alpha j multiplied by ha, and then it will generate the context vector here. So here it is called attention layer. So now we know the scoring functions, which is I have discussed, like Badhanu 2015, this one. So before Badhanu attention representation, there was also used attention, which is this scoring function. It's like cosine distance between source state and the hidden state. So there is source vector representations, state vector, and the hidden state vector. The how much distance between them, between two vectors. So this will provide some attention score. So now this function is modified by Badhanu, and it was very successful. And later on, this scoring function was is more simplified. And now, so for example, this is a Luang in 2015, he proposed the scoring function like this. So, and this one is the softmax. So Badan also using the softmax also, but this is the main function. So there is like source and hi, they are the cross product, dot product of between source and target and weighted by some matrix, which is trainable during the training process. And then it is again simplified. It is called dot product. So just it is not using the source, weighted matrix. And this dot product matrix is further used in Vaswani in the transformer uh, attention model. The attention all your needs. It is very famous paper now, and it is using the same dot product attention, but it is scaled by number of inputs, dimension of hidden state. So uh, so for now, maybe before was okay. So now maybe we can see an example for dot product attention. So in to calculate attentions, so we have three different vector now. So one is from query vector, which come from the output state like ST we have seen before, and the key and value vector come from the encoder side, like H vector, what we have seen before. So these three things are required to calculate the attention mechanism. So in this case, so for each query and key pairs, calculate the weight and then normalize to add to 1 between 0 to 1 for using a softmax function. So for in this case, if you say query vector come from the decoder state, and it has if you want to align head with some of the input word. So in that case, for example, A1 is calculated. So A1 is here is alpha ij, what I have told before. So this A1, so it has the information from the key vector, and then it is multiple dot product of key and query. That is A1 is generated. It's like this for the all the other cases, and then we have a softmax function, and then it is multiplied by value vector. So this is the name for so this scale dot one, sorry, the dot product cases. In that case, it is then multiplied by value vector. So value vector come from the encoded side, and then it will be generated like this. After softmax, it will be multiplied by the value vectors, which is the same like key vector in general. So then it will combine together with the value vector. So as I said before, so these are the value vectors. You can see that it is coming from the same source, encoder, and this one is the value vector is multiplied by all the encoder H1 information, like state, this H1 state coming from the hidden state from the encoder, and then it will multiply and it will generate a weighted sum for the attention score. So maybe you can stop here. So if you have some questions, then you can ask me, then we can proceed further. Any questions? Am I audible till now, or it is the connection close?
Yeah, you're audible.
Yeah. So
If there are any questions from the audience, please raise your questions. Are you able to hear? Some of you can.
Sir,
Uh,
sir, I have one doubt. What is the difference between an attention feature and a CNN feature? Why we are going for attention? Like, what is that difference between these two?
attention features and CNN features. Sorry. Hello.
Hello,
Yeah, CNN
sir.
feature. Yeah. I mean, do you know? I mean, you want to say CNN features and attention features?
Yes. So we have CNN which extract the features from an image. In
Hmm.
addition to it, we are using attention. So what is attention? Is like it's a feature or it's a what attention is supporting?
Yeah, so attention is different than CNN. So attention is just so in this case, if you say this is a bidirectional RNN, so if this bidirectional RNN produce some vector like HI and forward and HI backwards, let's say. So, and based on this representation, attention is calculated. Okay, so if you replace this RNN with the CNN, like convolution and sequence to sequence model, if you apply, and if hidden state, if each hidden state is the representation of CNN, and then attention is the different layer, not like so if you use CNN as an encoder, and a CNN will produce some features vector, and based on this feature vector you can calculate the attention between the CNN hidden state and the CNN decoder state. Sorry, CNN hidden state of encoder and CNN hidden state of the decoder. So between two, so attention is not related here completely some architectures like CNN or RNN. It is, you can apply either attention in CNN or RNN. So is it clear?
Yes, sir.
Okay, so let's see. Any further questions? So now let's proceed to attention mechanism category. So there are actually four categories. So here it is self attention and cross attention, and also global versus global attention and local attention, and hard attention and soft attention. So till now we learn global and soft attention, so which is very similar than what we have discussed. Now we will discuss local or hard attention and self attention and cross attention. So now start with hard attention. So after calculating, so assume that we have calculated the attention weights. So what we have discussed before. So we have now the weights of attention, calculate the weights, and now we could select the encoder state which has the highest attention weight. Okay, and these weights will be used in the context. So before we have taken the all the sum of input state. So let's see here. So here, so if you sorry here. So this context vector is taking the all the so j equal to I to 1 for tx. Sorry, this one also. Yeah. So all the hidden cells, so tx the length of the input, and this context vector taking the all the weighted sum of all the input. So in hard attentions, you are not focusing to all the inputs. You just focus on the only the sum of the subset or the or a single one which has the highest attention weight. So let's say for X2 has highest attention with YT through this connection. So let's say T2. So you are now only focusing on this one. So the will be this calculation will be less. So you are, instead of taking all the information, you will take this only this connection. So in this case, this is called hard attention. So let's say here, that is CJ, that's the context vector, will be taking the argument maximum, maximum value of based on alpha j, which one the maximum attention link among these hidden layers weights. So only one will come, the best weights will come, and then CJ will choose. So like instead of taking all the summation, it will choose the best one, which is not the case for the soft attention, where where CJ will be the weighted sum of all hidden input hidden layers. But what is the problem here? The curse of hard attention is it is difficult to incorporate. Although it is very simple and simplified, like so you are getting the best probable word between best probable alignment word between source and target. But in this case, it is very hard to incorporate in neural network actually. So as the neural network is a fundamentally mathematical function, and so this actually a heterogeneous composition of multiple small functions like layers. So layer wise, it will calculate all the function, and then if you could represent this network as a function, then function is expected to continuous and must be differentiable, so that you can backpropagate and your weighted value can be weighted gradient value, or can be adjustable or fine-tuned during your training process. So that hard attention is not easy to implement. It is very complicated for neural network cases. And also you have the operations used in selecting the most relevant encoder state is not continuous function. So the final conclusion is it is not differentiable. So how do we implement hard attention? So we'll come later when we are talking about local attention. So let's see the difference between local and global attentions. So this is the left side is a global attention, and the right side is local attention. So here global attention is exactly similar with what we have discussed before. So it has all the informations weighted sum, like context vector is the weighted sum of all the hidden layers and the attentions alpha t. But in this case, so if you see, there are a subset of hidden layer are providing the informations of the weights. So because it is called local weight, because it has only some localized hidden state providing the information. So instead of taking all the things from the hidden state of the input, here it will be that some subset of the hidden state. Okay, so this is the difference. And now, so global attention is the same like this before. So now local attention here. So it is, as I said, it is allowed to decoder to pick at a small segment of the source sequence, so that decoder could selectively focus on the token in that small segment. But here is the question is, which segment to select. So we have let's say 10 words, 10 sequence, and you have to select a segment among these 10 words. So which segment you have to select? You don't have any base now currently. So now there are two level of selection of segment, selection of search of segment here. So first we need to select a segment to pay attention to. So a segment where the attention weights are high. And then we select the token in the segment to pay attention to. So after selecting the segment, then we select a token where the highest attention will be measured. So what would be the segment size? So this segment size is like a hyperparameter. You can choose like any 3, 4, 5, but it should be empirically selected. Like you have to set either 4, 5, 6. So which is performing the better by tuning your hyperparameter value D. So now the this one, the segment size in according to the Luang 2015 paper, he has selected the dimension is like 2D plus 1. So this one is selected, and this is like a segment length of 2D. D has some value, is empirically selected, and this is the, I mean, double the size of D plus 1. Okay. And the number of attention weight is now fixed. And depends on D. So within D, the attention weight will be calculated. So instead of taking the entire source sequence length, which was we have used for the global attention or normal attention mechanism, what we have already learned. So now for the details. So the algorithm for the local attention. So in order to select the window of interest, we need to correct the place a center of window. That's mean we need to select a token or locations of the source sequence which will be the center of the attention. Okay, so what is the problem here? So we have run through with the hard attention again. So we have to select a particular location, particular token, a particular hidden state where we have we will get the much attention, and the same thing, same problem is happening now. It is a non-differentiable, so we can't back propagate or use the gradient value. So, but Luang proposed a clever hack to circumvent this issue. So in the next slide, I will discuss. So this center of the window is called, it is a token, it's called a predictive alignment, PT. So how we are selecting the PT and how we can, what is the hack to make it differentiable. So in this case, the first we see how do we calculate the predictive alignment token, predictive position, you can say. So this is the equations. So you have you have to select PT, then you have to so PT is 0 to S. S is the sentence length. So between sentence, you have to select a particular token, and based on this equation, hyperbolic tangent weighted with the hidden state of the t timestamp, it will provide the informations of the predictive token, and it is also trainable. All the parameters, like all the weights, are set during training process, so that after training some epochs, it will provide some provide the position of the predictive alignment token. And when you get the predictive alignment tokens, you have all the not only a single predictive alignment token, you have some good, let's say some subset of predictive alignment token, and you use Gaussian distribution in that case, which is continuous function from minus negative infinity to positive infinity, and you are empirically select a standard deviation, because this is the Gaussian function equation, and this Gaussian function you need a standard deviation. So this standard deviation value is empirically selected by d by 2. So d is the window size, and then this Gaussian function will multiplied with the alignment functions between the decoder state and the alignment function is nothing like a distance. It is the attention score between source and target. So this alignment function is multiplied with the Gaussian function, and then it will provide the alpha t or attention t uh, score. So that this function, this is an exponential function, and it could be differentiable now. So this is the hack. So how you can use the attention weights in local attention mechanism, how it could be trainable. So now what is doing in attention function? So if you see alignment weights HT and HS, here here you can see the weights between 0 to 1. So the probability, let's say here 5 is the highest probability, and then if you multiply with Gaussian function here, so this is the Gaussian function is like a bell-shaped function, a bell-shaped curve, and then if you see here, so this is like this, so highest weight is like U. So here is the center of word. I mean, it is considered as a PT. So the highest one, so that you can calculate your attention weights and context vector, and you can train your neural network through gradient propagations, back propagation, and gradient calculations. So now we have self-attention. So self-attention is and cross-attention, the basic attention mechanism calculation is same. So, but the input are different. In self-attention, your input on the same source sentence. But if you consider the cross-attentions, the input will be coming from the source sentence and the target sentence. I mean, input coming from the input sentence and the target sentence, output sentence. So in this case, self-attentions, so there are I will discuss later probably in details, but you can you just understand what is doing self-attention. So self-attention is about attending to word within the sequence, such as within encoder either or within decoder. So it will see that how the word attend to other words in that sequence. Let's say this example. So for the first example is the animal did not cross the street because it was too tired. So here it is referring to the animal in the very first sentence. So because animal was too tired, right? If you just change the word tired instead of wide, then what happened? So this tired, you just replace a word with wide. So the animal did not cross the street because it was too wide. So in that case, if you see, it is referring to the object instead of the subject. So the street. So attention is focusing to the relations also. So it will provide the information that this animal will be related with this, it will refer to the animal, and this in this sense the same sentence, but this it will referring to the street. So like this, so different it is a different example, but in this case it will see the relation. So it is related to apostrophe, so it's though, so that there is some relations, and though is related to the fantastic also. But it can also receive the information from Bart, and Bart also receive the information from fantastic. So this kind of information can be provided through the sentence. If you train your neural network with self-attention, so you can easily identify the relation and between the words in a within a sentence. So the entire representation of the sentence will contain all the information of the word, and also it could be applied to the any NLP applications, not only in machine translation but also sentiment analysis, sentence relation extraction, entity extractions, all those things you could be use self attentions is performing very nice, very better, and it is leading to all other applications, all other methods. Now the details about self-attention we will discuss in transformer model. Also we will discuss multi-head attentions during transformer model. So now let's begin with transformer model. So in transformer model, you have a model, you have an architecture, you have an input sentence for a source, let's say in French, and the target sentence will be in English. So, and this transformer model also following the encoder decoder trends. So encoder encodes the input sentence, pass the information to the decoder, and decoder will generate the output sentence. Now the architecture. So this one, the very known architecture, this is the original paper from Bhaswani 2017, and this one is actually proposed, and this one is nowadays very popular and high performing model. It is applied in so many applications, not only in the machine translation. So the paper was in machine translation, and also they have applied question answer, but currently it is applying a lot of things like in BART also, in language model, all the things, all the NLP applications are using this architecture. So now it has an input and output, and the next word will be next word of the output will be generated like this. So while training, you have source and target, and both and this one, the left side is the encoder and the right side in the decoder. And before going to the encoder or decoders, it has some input embeddings. I think embeddings has been discussed before in your lectures. So embeddings is like nothing, it is like a related word or of a particular language, in this case are are very are staying in a distributed place are staying in very less distance. If you say in words, in one word you can say this all related word, for example, so synonymous word, their distance in a distributed space, it is very less than compared to the antonym words, let's say. So input embeddings will happening, and then a positional encoding, and then a encoder where there is a sub layer is multi-edge attention, then feed forward network, and then this pass information to the decoder, and decoder is the like the similar when it is decode the decoder input sentence, and then it's perform the cross attentions, so across the language. It is called cross attention. The theory is same, like calculation is the same like self attention, but the query coming from the decoder, and then finally generate the output. So let's I will discuss more details in our subsequent slide, but if you see here in X here, so nx is the number of layers of encoder. So this is a particular single encoder. So and the very first encoder will receive the information embedding and positional encoding information is passed through the encoder, very fast encoder. And here it is the stack of 6 encoders here. So very first receive the information directly from the input, and the subsequent encoder are receive the information from the one layer before, like first encoder pass the information to the second encoder, and then third encoder, and so on. And the final representation will providing to all the decoding layers the encoder information. This all the decoder layers are receiving the same information from each decoder, and decoder also like this. So decoder also a stack of 6 layers, and from the from the first layer it will receive the information from the target sentence, and so on, and it will generate the output. So now in more details, so for particular, let's say this encoder, the very first beginner encoder, it receives some input and the output, and it contains self attention and feed forward network. So just simplifying this architecture, and it is also self attention and feed forward, but there is a cross attention layer, which is the attention between encoder and decoder. So now self attention in details. So let's say we have a sentence like x1 x2 to xt, and it will provide input vector. In this case, it is not actually the input vector. So let's say it is just the input vector for the attention layer. So this input vector, and it will provide some output vector y1 to yt with and which has dimension of k. Okay, so this is the known things you know. Okay, so this is yi is the summation sum of weighted of all wij. Let's say you have seen it is alpha ij at the beginning. So this is weighted sum of all input layers, or all input words, or all input hidden layers. And how this w dash j is calculated? So this is exactly similar what you have seen before. So this is the softmax function, and this wij is the attention weight, and attention is performed between within the x instead of input and output. So for example, xi for all j. So for particular word xi, how it is related to all other xj, it is the cross product. It is the sorry, dot product. It is the distance between xi and xj. So now in a pictorial representation, let's x1 to x4 is our input sentence, and x1 is providing some, it is it's multiplied by weighted matrix, and it is x2. Then just a moment, sorry. Just a moment.
Okay, Dr. Santanpur, no problem.
Okay, so
Yeah, we can understand actually.
yeah, yeah. Okay. Okay,
So,
now, yeah,
yeah,
sorry,
please
yeah,
go ahead.
go ahead. Yeah. So now we have a sequence of input x1 to x3, x4, and this vector is then multiplied by the weighted matrix W21, which is calculated through so x1 and sorry, yeah, let's say we have to represent y2, which so y2 is focusing on which vector, which input word actually. So let's say our focus on x2. Okay, so this x2 is multiplied with x1 for this case, and sorry, cross product, and then it provide W21, so like alpha, sorry, like a scoring function, you can say. So, and this is multiplied with the x1 in this case, so that it can generate all the sum of all the among attention weights, and then doing the softmax function here, all the summation are weighted sum, and then it will generate the relations of other, not only y2 for others. So in this case, you can see the strong attention weight, and in this case, other word, you can see the less attention weight. So always it is shown that always in case of self attentions, always the same word will get the more attention. It is normal, but during training, the other word also you will receive some attention score. Okay, so now, so for this case, let's say, so here all the input words are let's say x1, x2, x3 represented, like j is A2, étudiant. It is the French sentence, and it's all the words are representation of x1, x2, and x3 corresponding to. And these are the vector, uh, and each after this, and each word is a dimension of 512. It is a hyperparameter. Okay. Yeah. And the size of this list of the hyperparameter can be set, and this one, so x1 to x3, it is a length based on the your sentence length. So from x1 to xn.
sorry to interrupt, Dr.
Yeah.
Santanu. Are
Yeah.
there any person in your house to take care of the child?
Yeah, yeah, sure. Yeah, that is something. So just a minute, I just come back. For, let's say in 2 minutes.
Yeah, yes, sir.
Okay. Okay. So sorry for the interruption. Yeah. So
Okay,
it is
no problem.
difficult from work from home. Anyway, so just a moment. Uh, okay. Yeah. So if you see the word input word from input French sentence, each word is represented in a box here. So let's say this one is a vector, and this vector size is based on a hyperparameter which is empirically either empirically set, or maybe you can use the standard like 512. So and each word is like a this sentence as is the length of the sentence, like x1 to xn. It is represented in specifically in transformer architecture. It is like a fixed it is empirically sorry, it is set among your highest sentence length in your training data. And the very first layer, encoder layer, as I said before, very first encoder layer will accept the word embeddings and the positional encoding informations, and the rest of the encoders will be directly connected to the other encoder, and it rest encoder will take the representation from the other one network, one encoder before, like this. So very fast encoder will receive the embedding information, and then subsequent encoder will receive the representation output provided by the previous encoder. Okay, so let's see some example. So if you see this 00010, this one is the uh, vector representation of the input word, particular input word. So let's say x1 here. So it is called one hot vector. So one hot vector is the calculations. How did you calculate the one hot vector? So let's say you have a four sentence, and if each four sentence contains like 4 words, so you have 4 into 4 words, means 16 word, and there will be some repetitions, some words like so this is a dog, this is a cat, this is a this is a monkey, like that. So during these three sentences, you have some words which are common, like this is a, and the rest in the three sentence. So dog, monkey, and cat. These three sentence, three words, and this is a. So you have 6 unique word, right? So in that case, this vector size will be one hot vector size will be 6, and if you represent this, so for example, this is a, so this will be a 1. Okay, so this is then is will be 2. So 0 1 0 0 0 is this, and 1 0 1 and the rest of the 0 is like that, like that. So you have each word has this one hot representation, and you then multiplied by a embedding matrix which is trainable in that machine translation scenario, or if it is pre-trained embedding matrix, then you have already have some value. But if it is not trainable, if it is not pre-trained, in that case it was initially randomly initialized. So each row and column has some value, and then during training process it will be trained, and these weights are tuned so that your embedding matrix will be learned. And then this embedding matrix multiplied with your input vector, which is one hot vector representation, and it will generate the embedded it will embed your source words, each of your source word. In this case, and the size is 3, but in general we said it is 512. Okay, uh, or maybe 1024, based on your how do you accommodate in your computer or something, laptop or something. So now back to self-attention. So this embedding will go to the self-attention network, and the process self-attention layer provides some representation and going through towards feed-forward network, and send this output to the next encoder. After this is the very first encoder, so you can see encoder, and then all the representations is passing through the next encoder. So in this case, now the self attention in details. So what I said, this is like the same, like query, key, and value. So, and each query and key value has some weighted matrix, okay, two-dimensional matrix. And in general, this dimension of let's say it is 64 for embeddings, and the input output vector have 512 dimensions. So this and this one 512, if you consider if you divided by 8, it will be 64. So the input dimension was 512, but query, key, and value dimension is 64. But why? Because in transformer architecture, they are using multi-head attentions, and they have in general they have 8 heads. For transformer base, you can also increase your input vector size and also increase the h value of multi-head attention, and then you can also this dimension also could be different, but in general it is h value will be 8, and this 8 is divided by the input vector, and that will be the dimension of query and key and value. So I will discuss multi-head attention later, so where you will understand why we use multi-head attention in this case and how it is benefit. So now we have some weighted matrix and some query. So each query have some weighted matrix, and if we multiply the weighted matrix, so like so we have input dimensions, but we have to make dimension of 64. So we have, let's say, this one 5 1 2. Okay, so in this case it is 4, but we have to reduce the dimension, so we will multiply the weighted matrix. This WQ to WK and WV, they are trainable. They will tune during the training process. So now if we multiply 4 x2 with sorry x with W, then it will it will generate a single vector for dimension 3. So like this. So the 4 row will multiply it by 4 column, and then it will be the output will be the 3 by 2. So if it is x, if x dimension is 2 by 4, then it will be by 2 by 3. So like this. So a similar thing happening for other query key value. Now, so input, embedding, query, key, value, and then for attention, we know that query and key value is a dot product. Let's say the dot product is, in this case, thinking machine. In this case, query and key is 112 and 96 for query thinking. Thinking and machine attention weights is 96, and thinking with thinking it is 112. So here note that this query and key coming from the same sentence, that is why it is called self-attention. While this query come from the decoder side, it will call cross-attention. So this query would be different in the in case of cross-attention. It will come from the decoder, but here it is in the as it is self-attention, it is come from the self sentence. It is using the encoder embeddings. So now the next process is, it will be scale, as it is transformer using the scale dot attention. So as I said before, it will divided by 8. So this is the value of the root over of dk. dk was something 64, because all these dimensions are 64. So that is why root over of 64, it is 8, and then it is scale in 14 and 12 in this case, let's say. So divided by 8, it will be 14, divided by 96, divided by 80, it will be 12. And then softmax function happening. So softmax, as I said before, softmax is providing the value between 0 and 1. So that here, if you sum this will be 1. So the probability of thinking, attending to self with thinking, it is a 0.88, and the probability of thinking attending to machines, it will be 0.12 in this case. And then it will be the weighted sum, like softmax multiplied by value. So which one? Then a value matrix, and all this sum will be Z1. This is the representation, final representation of the self-attention layer. So in this case, similarly, when we calculate a machine, it will generate the representation, self-attention representation Z2, like that. So Yeah, so how Z was calculated? It was like a softmax function, as I said before. So softmax function here, and then multiplied by value, and then it will represent Z. Okay. So now multi-head attention. So why we use multi-head attention? So it's actually it expands the model ability to focus different position. Okay. So if you have only a single calculation, in that case, you will get only focus. In this case, if you see here, in this case, uh, this will focus only just thinking. So, but it could be related to other word also. So maybe they during training time they have occurred together many times. So there should be there some relations. So in that case, to achieve that, so we have randomly initialized these values in four different time. So for example, Q1, so the weight matrix or W0 Q1 and W1, sorry, W1 Q and W0 Q, they are randomly initialized and their value not the same, they are different. So after multiplying Q0 and W0, the representation will be different. And these two head, so that will be the 8 head I said. Let's say now we have, for understanding, we have now 2 heads. So this head calculation, attention calculation, and this head attention calculations provide some different information. And like that, so if we have 7 heads, so we have different representation of Z. So this and they are independently attention calculated. Uh, so all the Z has different information, and then we present, concatenate together, and then multiplied by a output weighted matrix, and then finally prepare the same size of vector with a we have to pass this representation to the feed-forward network. So feed-forward network receives some size of vector, so we have to scale this. So that is why we multiplied some another trainable weighted matrix, which will after multiplication it will provide the output vector like this. So 4 cross 4. So finally we have 2 cross 4. We have the input same dimension like the input matrix. So now to summarize, the first thing, we have input sentence, we have embeddings of this input sentence, and then we have different head, like in this case 7 head, so, and multiply input matrix to make this 7 query key values. And from query key values, we have some self-attention representation, like 7 different representation for head, attention representation, self-attention representation, so Z0 to ZZ. And then we multiply with concatenate all together and multiply the weighted matrix, and then finally represent the same size of the inputs like this. So Z. And now it can, if you see, it has some relation. If it is too tired, so it can identify the strong relations between state and tired. Okay. So now the positional encoding. Okay, so far we have time 10 minutes. Okay, so maybe I can just quickly complete and then we can. Yeah. So there is a positional encoding here. So if you see RNN, so there is some information flowing from very first word to end word. So in that case, all the word has some information of the previous word. So, but in this case, there is nothing. So that is why we need to inform this transformer network the sequence of the input words, because during propagation it could be there is the possibility to forget the sequence. So that is why this positional encoding happening. So positional encoding is providing the information of the sequence. It's like the first word, second word, third word, like that. So this is the uh, encoding of the position of words. And again, this is only going to the encoder 0, not to the all the information to the other encoders. So 0 to passing to the subsequent encoders. And it is calculated with a function. I would not go much details on this. So there is some function which can calculate like it is there is a sine and cosine function with the dimension of single dimension. And there could be possibility, because you have 6 layers, 6 encoder layers and 6 decoder layers. So there could be possibility to forgetting. So that is why you see some residual connection. Residual connection means skip connection. So after calculating self attention, there could be possibility to some information loss. So that is why we can directly pass the information for positional encoding. After the positional and word embeddings, we can directly pass the information after the self attention, and then we add them and do some normalizing technique so that it can pass to the other sub layers. Let's say sub layer, this one, the feed forward network. And after feed forward network, it could be also possibility. So that is why for safe side, we also pass the information again through by skipping the feed forward network also. So it has both informations of the previous layer and the current processing of information, and then pass to the next subsequent encoder and then to the decoder. So here you can see the pictorial representations, how it is working through the encoders, and then encoder decoder vector multiplications key. So if you see this is a key and value coming from the encoder, and and the query coming from the decoder, the cross attention performing here. So it is exactly same like self attention, but the query is coming from the decoder Q value. So this is the entire process, how it is working. So if you see the first from the second step, how it is generating the output, how it is training, and then after time step 6, it will end the sentence, and that's all. Maybe you have a lot of questions. You have some difficulties to understand something, so let me know, please. I can explain again.
So if there are any questions, please raise your questions.
Sir, good morning, sir.
Good morning.
Sir, regarding the auto and encoder and decoder,
Yes.
If the class level is there, can we apply that model, sir?
For auto encoder, right?
Yes, sir.
Yeah. So for auto encoder, so let's say I can explain through this architecture. So for auto encoder, so you have some noisy input for some noisy text to make it sentence. I mean, if just correct the sentence through a noisy representation. Okay, so in that case, you can also use this one. So you can just change the input with some noise value, and the output is the actual representation. Then it could be used as a autoencoder. But for autoencoder, it has encoder decoder architecture, and then you need some different loss function. So in this case, you can use any loss function in this case, but also you can use scale divergent, for example. But for specifically autoencoder, it is also like encoder decoder architecture. You can implement any architecture like RNN or CNN, but you have to use different loss function like KL divergent.
Thank you, sir.
Yeah.
Sir, I have one more question.
Yeah.
Is this transformer applicable for classification purpose, time series classification?
Yeah, you can use time series classifications, but in that case, you have the output for output value will be different, right? So like if it is multi-class, then I think it will perform better. For two-class classification, I think this will be too much to include transformer architecture. So it just you can simplify the transformer architecture. So you don't need to use on the output side is a sequence to sequence model. But for multi-class classification model, I have seen some papers they are using transformer model, but they are customizable. Yeah.
Okay, thank you.
Yeah.
Any other question, please? So if there are no more questions, let us thank Dr. Santanpal for his illustrative description of attention models, its variants, its applications, so on. And I am sure that this talk has given us a sufficient inspiration to explore the field further. So thank you, Dr.
Yeah.
Santanpal.
So I must say sorry for some disturbance.
That's okay.
Yeah.
That's okay. That is natural, na? Because
Yeah.
anyhow, we are dealing with natural language processing one thing.
Yeah. Yeah. Okay, thank you so
That's
much.
okay. No problem. Thank you.
Yeah.
So to the audience now, the announcement is that we will take a break at 11 o'clock, and we are going to come back at 11:30. And in the afternoon, we are going to have assessment examination for you, and after that there will be valedictory function where our director will be addressing. So you can see that schedule, whatever schedule link I have given. If you want, we can resend the schedule link. So now let us take a break. Is it okay?